Okay, welcome back, everybody. Last time I had begun to talk about Tartaglia and Cardano. Um, so, um, so their contributions are intertwined because it is to both of them that we credit the solution of the cubic. As I posted in an announcement earlier, today I uploaded a lecture that's kind of a standalone lecture that goes over exactly how they did that, as well as how the general Quartic was solved. So Tartaglia and Cardano um, were responsible for solving the general cubic. If you want to see exactly how this was done, you can check out that supplemental lecture that I uploaded. So general cubic, after we've divided through by its leading coefficient, this is x cubed plus ax squared plus bx plus c is equal to 0. So this is what I mean when I say general cubic. Okay. This was a joint effort because, as I outlined in that supplemental lecture, Tartaglia had this trick that he had devised for taking this general cubic and basically shifting it to be something that is a little bit more specific, and it's something that ultimately he knew how to solve. So this method, he had figured out from his earlier encounter with Fiore and this math contest that I mentioned last time. And so Cardano had actually basically been in contact with Tartaglia about this method, and Tartaglia had told him his secret method for doing this under the condition that he never tell anyone about it. And later, when Cardano actually discovered that it was due to Tartaglia and this previous mathematician Fiore, once he realized that this method was not that secret, it had actually already been out in some way. Cardano published it in his big work that I'll talk about here in a second, and Tartaglia was apparently really, really furious with him over this. And whether or not Tartaglia spent the rest of his life in like a feud with Cardano is not necessarily supported by the evidence, but that's kind of the legend, is that they were in a bitter feud until the end. So Cardano was born in 1501 and died in 1576. What is notable is that he was the first to write in detail on imaginary numbers. So first to give detailed algebraic description of imaginary numbers. Again, if you check out that supplemental lecture, some very basic facts about imaginary numbers and their arithmetic are required in order to write out this general cubic solution. Anyway, so Cardano was kind of the first to actually write out imaginary numbers in this way and deal with them algebraically. The best example of this is in his most famous work, which is Ars Magna. So this was published in 1545. And it is in this text that both this method of solving the cubic, which is credited, so credit is given to Tartaglia in coming up with this trick and in contributing to solving this cubic. And also, what's included in Ars Magna is a solution to the Quartic, which was due to Cardano's student Ferrari, that I'll talk about here in a second. So this is the best algebra book at this time. So when this is published, This is kind of the first step up from Diophantus, since, well, so there's like a 1300-ish year gap here between Diophantus and the Ars Magna being published. So this is kind of the new best algebra book when this came out. So here's a little bit about Cardano before I move on, because this is pretty interesting. Cardano was originally a famous physician, and actually apparently had traveled to Scotland to cure an archbishop of asthma, supposedly. His oldest son was executed for having poisoned his wife, and Cardano himself was imprisoned in 1570 for heresy for having published a horoscope of Jesus. And this is deemed heretical because it suggested that God was subject to astrology and the stars. Okay, so that was considered heretical. But he was released eventually after he recanted. And so supposedly he also foretold the day of his own death, again using astrology, and then felt compelled to commit suicide to make his own prediction come true. So I don't know whether or not that's true. This is part of the legend of Cardano. This is there was a biography of Cardano that actually I think it was an autobiography. I think he wrote it himself. That you can have a look at. I'm not exactly. I haven't actually read it myself, but yeah, apparently there's an autobiography of Cardano that you can. It's been translated to English for years now, so you can have a look at that. Okay, so a couple of things specifically about the Ars Magna. There are proofs of, for instance, algebraic identities, like a minus b cubed is a cubed. So a cubed minus b cubed minus 3ab times a minus b. So an expression like this, which could be proved algebraically, is actually proved geometrically, right? Like in an ancient Greek style. Again, these types of expressions are being viewed kind of geometrically, which is a very much ancient Greek way of looking at it. And also, despite including a description of imaginary numbers and how to deal with them, it actually tried to shy away from the use of negative numbers. And so, for instance, to give you an example of what it means to shy away from negative numbers in this sense, so the equations say x cubed plus px is equal to q, and the equation x cubed is equal to px plus q, and the equation x cubed plus px plus q is equal to 0. All of these would have been written separately, right? Like they were separate equations. Another one, like x cubed plus q is equal to px. All of these were treated separately. This is very similar to how some of the not ancient, but the algebra textbooks, like some of the Islamic mathematicians wrote. This is very typical of how these things were treated. Due to them being a little bit skittish about using negative numbers, these equations would have been treated separately. Okay, like they were totally different, despite having the exact same form, right? So we recognize that there's no reason to treat all these things separately. We can actually just say all of these have the same type, right? All we care about are the coefficients on the powers of x here. If we're talking about some cubic expression, we don't care, right, about these signs necessarily, but these were all considered very different, completely different equations here. Okay, so the Ars Magna contained an account of the cubic equation, but it also contained an account of the quartic equation. And so a solution to the general quartic equation was due to a student of Cardano's who's Ferrari. Okay, so Ferrari Um, let me see here. Ferrari was born in 1522 and died in 1565. So he was a student of Cardano. And he solved the general quartic equation, which looks like this after I've divided the leading coefficient. Ben, so they would not like x cubed plus px minus q equals 0. Yeah, exactly right. Because you either have to say a couple things there, right? If q is positive, right, then so if q is positive, then you're subtracting that positive number there, and you have a since q is positive, that operation you're doing is like having a -1 coefficient there. Of course, we know that it's the same as subtracting, but they would have been a little bit skeptical of having that as a general expression for that equation. Yeah, I would say that when they were writing those expressions, they were always considering the p and the q showing up to be not just real, but also positive. Okay. So yeah, this was, it's one of those things where it's funny to see what they were caught up on, especially seeing as how, when you actually see how complicated and convoluted some of these derivations were, it's funny that they were so caught up on things like that. So the general quartic looks like this. Okay, so here's the general quartic. And so, to explain how the cubic was solved, basically, there's a trick that Tartaglia uses to rewrite this as a specific cubic where the square term is dropped out. And then it gets reduced to a quadratic thing, which of course we know how to solve by the quadratic formula. And we have radical of a radical. So we have a cubed root of something that involves a square root. Okay. So similarly, this gets reduced to a cubic, which I can solve. That cubic leads to a quadratic thing, and I'm going to end up taking a square root of a thing that also has a square root. And so that's kind of the idea. There's almost like there's this reduction argument that gets done. So for this one, there's a completing the square thing that happens. For the cubic, that's not exactly what happens. It's that Tartaglia trick together with, there's something else that's required that turns it into a quadratic thing. But basically what you're doing is you're reducing the order of the problem or of the equation that you're having to solve, is kind of a way of thinking about it. And so a natural question then is whether you can continue to do this. And as I've already mentioned before, it would take another couple hundred years, it would take another 250, 300 years before it was realized that no, in fact, this is as good as you can do. So when we say solved, we mean it's an explicit solution in radicals in the same way that you have a solution for a quadratic equation. So solved via radicals. What I mean is that this is a totally general thing, and it is solved in the exact same way that we say the quadratic equation is solved, right? So if I give you a quadratic, you can always use the quadratic formula to find the roots of that thing. So in the same way, for the cubic and quartic, there is a closed form expression in radicals, right? Some nested radical thing. that is a solution for these things. But for quintics and so on, so for the fifth order general equation, there is no such formula. It can't exist. But that wasn't shown to be the case until much, much later. Okay, this is due to Galois, Abel, and Ruffini are the ones that showed this. So later, maybe I'll say, it was shown, so this is due to Abel, Ruffini, based on the work of Galois, that degree 5 and higher equations cannot be solved in this same manner. And so this is as far as you can go. Okay, now the question is why degree 5 matters. It's hard for me to give you a satisfactory answer. This question ultimately led, Galois was the first to work on this. Galois formulated something that would come to be called group theory. It was the notion of what's a mathematical group. So this was done via group theory. Group theory is an outgrowth of Galois and his work on, I can't remember if he used the word permutations, but it was on permutations of the roots of a polynomial. And it turns out that the problem with 5 and higher is that the associated group that is associated to the roots of these polynomials is large enough that it contains subgroups that are naughty, okay, in a sense. And when your degree is 4 or less, you don't get those, okay? And it's the existence of those things that cause this to be bad. Now, why that would have anything to do with this is a little convoluted, and it's kind of far removed from this question. But there is a straight line between considering roots of polynomials like this and the foundations of what's called group theory. Okay, so this was kind of, once you get to this point is when you're doing like modern algebra. Okay, so this is group theory is the first thing you will touch on when you take your first serious algebra course in math. Okay, so it grew directly out of the theory of equations here. Okay, and so Ferrari's result on solving the general quartic was actually included in, so this was included in Ars Magna. Okay. So supposedly Ferrari was, the reason for his early death is that he was murdered either by his sister or by his sister's boyfriend. So that is supposedly what happened to Ferrari. Okay, so there's Bombelli. It was a contemporary. Bombelli published an algebra book in 1572, so the same year of his death. So published an algebra book in 1572, tracing the history of algebra, or the history. So tracing the history of algebra all the way back to Diophantus. He discussed more about complex radicals. So discussed complex radicals. So this discussion leads exactly to what we do in case 3 of the supplemental lecture. So case 3 of the cubic solution. You can check that out in the supplemental lecture. And he also showed that, so he was the first to show that the Greek angle trisection problem is the same as solving a particular cubic. Okay. Now, it wouldn't be until a little bit later that the compass and straight edge constructions would be tied in with how to actually, whether or not that cubic could be solved via compass and straight edge constructions. This was something that would come later, but he was the first to tie in the Greek angle trisection problem, which is a problem in geometry, to solving a cubic, right, which is just directly out of the theory of equations. Okay. And one more thing, notationally, he wrote this little arc symbol with an n over it for the expression x to the n. Okay. So I don't know too much more about this guy. The next, so Francois Viette, or Viette. Okay, it shows up as both. So he lived from 1540 to 1603. He was a French lawyer that just happened to be really interested in math on the side. So he wrote a book in 1591. So his book is in Artem and Analytism Isagoge. This is in 1591. So this included a couple of things. So one, both of these things are called Viette's formulas, by the way. So I'm going to write the one that is usually called Viette's formulas first, and then I'm going to write Viette's formula singular. So there's Viette's formulas. So the idea is if p sub n of x is a generic nth degree polynomial, so it has leading coefficient a sub n x to the n plus a sub n minus 1 times x to the n minus 1, and so on, all the way down to a sub 1 x plus the constant term a naught. Okay, then there are formulas relating the roots of this thing to certain combinations and ratios, I should say, of the leading coefficients, or various coefficients here. So maybe I should be more careful. So suppose the roots are, we'll say, x sub 1 to, well, let's call the roots r sub 1 to r sub n. R sub 1, r sub 2, and so on. We got to r sub n. So writing with multiplicity, we can always do this. This is due to something called the fundamental theorem of algebra. So the fundamental theorem of algebra says that if you have a degree n polynomial like this one, how many roots does it have? That is, how many solutions to the equation p of x is equal to 0 are there? For an nth degree polynomial, there's exactly n, so long as you take into account a couple things. One, you don't care if they're complex or not, so complex roots are fine. Okay, and secondly, you count with multiplicity. What that means is that for a polynomial, there exist roots that are roots with multiplicity greater than 1. So there's the notion of like a double root for a quadratic. So imagine you have a parabola, but instead of crossing the x-axis in two places, it just comes down and is tangent to the x-axis somewhere, right? So technically there's only a single root there, but we call that a double root and we count it twice. So in this list, I'm not saying these are distinct. Some of these could be repetitions. But if we count with that repetition, there's always n. This is the fundamental theorem of algebra. Okay, so if we do that, then I have an interesting set of formulas that relate algebraic combinations of these roots with the coefficients here. So if I sum all of these roots all the way out to r sub n minus 1 plus r sub n, if I sum all those roots together, that is equal to minus a sub n minus 1, which is the second, it's the coefficient on x to the n minus 1. So it's the penultimate coefficient here, divided by a sub n. Sorry. So summing all of the roots together, this is minus a sub n minus 1 over a sub n. If I multiply in pairs here, so if I multiply r1 times r2 plus r1 times r3 and so on all the way out to r1 times rn, okay, and then I add to that the same kind of multiplication in pairs, right? So r2 times r3 plus r2 times r4, right, skipping the lower indexed things, then plus you say r2 rn, and I keep doing that, blah 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 and so on. What do I get? This is equal to a sub n minus 2 over a sub n. Now it can be a little bit hard to see this pattern, but if we carry this out and we keep doing this, ultimately trying to come up with these terms, I'm just going to get to the end when I do a long product. So the next line I would do triple products here and sum. Okay, but in the last step, I'm just going to be multiplying all the roots together. So this is, the thing I'm about to write is probably the most commonly used Vietnamese formula. So this is r1 times r2 times r3 and so on all the way out to rn. If you take all the roots of a polynomial listed with multiplicity and you multiply them all together, you get minus 1 to the n times a naught, that is the constant term, over a sub n, which is the leading term. This one is probably the most commonly used and in some ways is the most useful. This actually has a ton of applications. So you might not be familiar with this, but if you've had linear algebra or you know what eigenvalues of a matrix are, you might remember that there's this fact that the determinant of a matrix is actually just the product of all of that matrix, matrix's eigenvalues. So determinant of a matrix A, so determinant of A, is equal to the product of all the eigenvalues of A, listed with repetition. Okay, that fact comes directly from Vietnamese formula. So this fact is exactly what tells you that. Okay, it's actually a really easy proof once you know this. And so that's one application I can think of off the top of my head. There's another cool thing that is called, and so Vietnamese formulas, this is something that Viète proved, and this is true for any polynomial. It has this relationship with its roots. So there is another Vietnamese formula that is kind of cool. So this involves pi. So Viète's formula says that 2 over pi is equal to the square root of 2 over 2 times the square root of 2 plus the square root of 2 over 2 times the square root of 2 plus the square root of 2 plus the square root of 2 over 2, and so on. Okay. Okay. So, actually, I think this one was published a couple years after that work that I mentioned. So I don't know if this one was included or not, if it wasn't published till a couple years later. So this may have been published a couple years later in like 1593. But anyway, so this is a formula. You can, if you like, you can view this as a formula for pi. In terms of this infinite product. Now, Vieta used this to actually approximate pi. So he used this to give an accurate approximation of pi. It wasn't the most accurate approximation of pi at the time. So, for instance, an Islamic mathematician that I can't think of his name off the top of my head, but a couple hundred years previously had actually written out an approximation that was, I think Viete's approximation using this was accurate to 9 decimal places, and the Arabic mathematician that I can't think of, his approximation was accurate to like 16 decimal places, I think. So it wasn't the most accurate representation of pi. Also, as I mentioned previously, even Archimedes knew a way of generating a method for approximating pi that could get you as close as you wanted if you were willing to do the work. So it had long been known, like processes for coming up with an arbitrarily close approximation of pi had been known since antiquity, really. So what was amazing about this formula wasn't that it was the greatest way of approximating pi or anything like that. And actually, Viete's idea here, how he came up with this formula, was based on Archimedes' idea. So he was directly inspired by Archimedes and this notion of inscribing figures inside a circle to come up with bounds. So inscribing so inscribing circle and then considering bounds on a polygon outside the circle as well. So anyway, so he used this to give an accurate approximation of pi, but this wasn't what was amazing. This was the first instance of an infinite product. So this was the first instance of an infinite product. Okay, being written down in a mathematical paper. All right. Okay. So that's another neat thing due to Viete. Okay. So I had previously mentioned that when you come across mathematicians in this era, very frequently you're going to hear various talk about astrology and how they were all into astrology in one way or another. And Kepler probably said it best when he said that the best way to make money in this field was to convince people that knowing the stars, like knowing something about the stars meant being able to predict the near future. And so his reasoning, paraphrasing, was that astrology paid for his astronomical observations. So he could fund his astronomy through astrology, so he had no problem doing that. And so this was, if you had your doubts as to whether or not they were really, really involved in astrology and really, really believed in astrology, at least some of them were a lot more cynical about it and just kind of viewed it as an easy way to pay the bills. Of course, there are always exceptions, and I'm sure many of them actually did believe, put a lot of faith in astrology. As I already mentioned, Cardano supposedly, used astrology to try to predict the day he would die. And later we'll see Newton, despite being a great scientist, spent like 20 years doing alchemy, long past the time when alchemy was thought to be something that that was workable. So you never know, right? You never know. Can't. Not all things are concentrated in one person. So, I had promised 4 big things in Renaissance math. So those were my first 2. Now I'm on to number 3, which is the discovery of logarithms. Why is that an A? That should be an O. So it may surprise you to learn that logarithms were something that were developed before there was a good notion of calculus, right? So you've probably only thought about logarithms in terms of basically after you already knew calculus, right? So you're thinking of it kind of from the calculus and at least knowledge of derivatives direction. And so how was it that logarithms were actually developed? So logarithms were developed by a Scottish aristocrat named John Napier. So he was born in 1550 and died in 1617. So he's a Scottish aristocrat, and he spent 20 years coming up with logarithms. So 20 years devoted to logarithms. And the thing that he would call a logarithm, when Napier says log x, what he means this thing that is 10 to the 7 times the log base 1 over e of x over 10 to the 7. Okay, so just to remind ourselves, so here's some modern notation. When I say log bx, the way I read this is log or logarithm base b of x. Okay. Now, if you look this up elsewhere, this expression is sometimes referred to as a Napier log, or some notation even writes this as nap log. So nap log x for Napier logarithm, which is this thing. Okay. Now, obvious question when you see something like this is why, when he says this, does he actually mean this? So if you recall some facts about logarithms, right, you'll recall the fact that kind of the most natural log is the natural log, right? That is the logarithm with base e, okay, which we know is called Euler's number. We're not to Euler yet, so we'll get to that a bit later, but kind of the nicest possible logarithm that you can talk about, or the most natural in some sense, is going to involve this e, okay, where e is Euler's number here. All right, so then why the reason for these other things here? So I'll first give a quick idea about what's going on here. All right, so what was a question? What was Napier's idea? Behind log x. Right, what was the idea here? Okay. Well, the idea is this. Suppose that I have the plane here, right? So let's say I have the plane here, and let's say that I think, okay, let's say that I have a point. We can think of that as a particle here. at x equals -1 on the negative x-axis. Okay. The idea is that this particle, let's label it, let's call it P. Yeah, so this particle P moves towards the origin. And let's say it moves towards the origin at a speed proportional to its distance to the origin. Okay? So it moves towards the origin at a speed proportional to its distance to the origin. So now you may have already guessed what is happening here. Okay, if not, then don't worry about it. But the hint I'll give you is that this is not the only way of coming up with this. So if Napier had never thought about this description, it doesn't mean that there wouldn't be logarithms. There's a number of ways of coming up with this. The idea of a population growing or decaying at a rate proportional to its population size, that is another way that you could have come up with the notion of logarithm. It's the idea here that speed is proportional to distance. What is the main thing that that's saying? We know now that speed, right, if we're using our post-calculus brains here, speed has something to do with taking a derivative, right? And so if my function in question is describing position or distance, right? The speed, its velocity or its speed, right? That is something I compute by taking a derivative of that function. And so really, this underlined bit is saying something about derivative being proportional to function itself. That's what this underlined bit is saying. Okay? And so what this is saying is that when I have some function that's describing position, let's call that function x of t, right? So I'm dealing with time here. The fact that I have a derivative of this thing that's proportional to the function itself, it means that x prime of t, or the derivative of x with respect to t, is equal to some constant of proportionality c times the function x of t itself. Okay. So if you have never had any differential equations, fear not. This one's simple enough if we just think about for a second. So if I tell you, right, that a differential equation satisfying certain initial conditions, so for instance this one tells me that x of 0 is equal to -1 here. So if I tell you that if I have this is an example of a differential equation. It involves derivatives of some unknown function. If I tell you that I've specified an initial value of this unknown function, how many possible solutions are there to such an equation? The answer is there's one. There's one function that does this. Okay, and you might have already guessed what function that is. It's the exponential function. Okay, using e. Okay, so it's the exponential function using e. That is the base of the natural log, Euler's number. Okay. So that's what's going on here. Okay. So where does the logarithm come in here? So forget about this for a second. So I'm going to box this off to the side. So forget about this for a second. Let's go back. So this particle P is moving towards the origin at speed proportional to its distance to the origin. Okay. So then what that means is that for any distance d, for any distance d to the origin. So for instance, let's pick here. All right, so here's my distance d. Okay. So at this point here, for any distance d, okay, there is a time we'll call it big T. So there is a time, big T, when the particle is that distance from the origin. It is exactly d distance from the origin. Okay. So call this t, so call this time t the logarithm of d. Okay. And so this is how I define a logarithm. Okay. Now let's go back to this description. Right. Let's go back to this description. So in this description, let's suppose that my constant of proportionality is 1. So when I say that the speed's proportional to its distance, I'm going to take this big C is equal to 1 here. Okay? And so, the way that I've written it here, we'll take it to be -1, right? Orienting this left and right motion this way is positive. Let's make this would be x prime is equal to minus x here. Okay, so let's let me get a new sheet. So take the proportionality constant to be -1 here. So this would be x prime of t is equal to minus x of t. Okay, and I still have that initial position. So my initial position is at -1. Okay. Then what is the function that solves this? This is called an initial value problem, an IVP. Okay, so what solves this? Well, if x of t is minus e to the minus t, I satisfy both of these. All right. If t is 0, then I get minus e to the 0, so that's -1, so that's good. And then you can just check, if I take the derivative of this thing, what do I get? I get minus e to the minus t times -1, so I get e to the minus t, which is exactly minus x. Okay, so this does in fact solve this thing. Okay, and so what is my time t here? If I'm solving for t, what is that? X is my distance d, so I'm taking the log of what? So here I'm saying that t, I'm solving for t here, this t is equal to minus the log base e of d, right? D being my, d replaces x here, it's my fixed distance. Okay, but using log rules, right, I can think of this as being really log base 1 over e of d. Okay. So for the rest of this little bit, so for the next comments, whenever I say log of x, I mean the log base 1 over e of x. Okay. All right. So I don't have too much time left, so I think I'll stop here. But what I want to do is show next time how Napier actually computed these logs, right? Because that might be the next thing, the next question up, you might say, is like, well, how did he compute these, right? Because your entire experience with logs, they're very mysterious when it comes to actually writing them out, right? So if I ask you to compute, right, the natural log of 3, right, I don't think most of you are going to just start rattling off numbers there, right? There's not like some quick way of computing this thing. You're relying on an actual, calculator or computer to spit out, decimal numbers for these things. So anyway, I will show next time how Napier actually computed with these things, and I think that will pretty much do it. I'll have another little aside. I wanted to mention a guy by the name of Henry Briggs, who basically was the first. He had long discussions with Napier, and he was the first to kind of convince Napier that the log base 10 was also something that was useful. And the reason I wanted to cover this now is because it's going to directly lead into the next thing, which is eventually Kepler's use of logarithms and Kepler's formulation of his laws of planetary motion. So anyway, that's where this is headed. We're almost, after we finish this discussion of, this is kind of the last Renaissance mathematicians I wanted to mention before getting into the 17th century mathematicians in France. There's a lot to say there. So anyway, we are soon closing in on, pretty soon we're going to be in the 1700s, which is kind of the last century where we can say a bunch of reasonable things about a bunch of different fields before things start specializing to such a degree that we basically stop being able to do this kind of universal coverage that we've been doing. Okay, so anyway, that's that. I will see you all on Wednesday. I'm going to have office hours for you to ask any questions that you might have on the midterm. So I'm going to have office hours either Wednesday or Friday, so I'll let you all know when that's going to be. And you all can ask kind of any questions you want. If those don't work for you, you can always make an appointment to meet me sometime in Zoom if you have specific questions. So either way, I'll see you all on Wednesday.